Okay, so what we're going to do on this problem then is we're going to start with the first derivative. This will be a pretty easy problem because the derivatives are easy. So that's going to be 20x to the third minus 60x to the second. Okay, then since we're analyzing concavity, what are we going to do? We're going to go to the second derivative. So you want to go ahead and do that. So what's that? 60x to the second, 120x, okay? Easy derivatives make the problem easy, all right? So what we do now is we set that second derivative equal to 0 to analyze the concavity. So we're going to solve the equation 60x squared minus 120x equals 0, okay? How do you solve that equation? Factor. You're going to do that a ton. Get used to it. Okay, you can take a 60x out. So you have 60x times x, and then minus 2 like this. Okay, can you tell me what the two answers to that equation are in your head? 0 and 2. Outstanding. Okay, sometimes you can, sometimes you can't. When you can, don't waste your time, just write the answer. So yeah, you're just going through and setting each factor equal to 0. So you would get 0 and 2 like that. So here's what you do then. You do a sign chart like what we were doing last time. So go ahead and just draw a number line. And what we're going to do is on the number line, put a 0 and then put a 2. And then we'll just sort of break this up into two regions like that. Okay, everybody okay so far? Okay, this is a pretty standard elementary problem because the derivative's not hard. Okay, now what we're going to do is we're going to do test points, but we're going to evaluate the second derivative. So here's the second derivative. It's usually easier to use the factored form of the second derivative when you plug stuff in. So when we do our test points, let's use 60x times x minus 2. And you can actually even ignore the 60, okay, if you want to, because that doesn't make any difference anyway. Okay, so just like we did last time, let's do test points. Let's use a number less than 0, like -1. Okay, if you do this, you'd have 60 times -1 times -1 minus 2. All right, now I look at this like this. That's negative, that's positive. Or no, that's negative also, sorry. Okay, so that's negative times negative, so what is that? Positive, okay? All right, so what that means, what does that tell you about the concavity? Concave up. Positive is smiling, okay? All right? So we are concave up, all right? Then we just proceed with the same kind of thing. You go through, take a test point here. Let's work with 1, okay? So if you do that, you'd have 60 times 1 times 1 minus 2, okay? Again, just do that. That's positive. That's negative, okay? So you'd end up having positive times negative. Negative, what does that tell you? Concave down. Okay, like that. See, nothing to it. Okay, if the arithmetic's pretty easy, it's not bad at all. And then the last thing we'll do is let's take a number bigger than 2, like 3. So we'll have 60 times 3, 3 minus 2. If you work that out, that's going to be positive. So that means you're back to concave up, like that. Okay? All right. Now, what we have on this then is we write intervals just like we did increasing and decreasing. So concave up occurred in these two places that I'm highlighting, and you use open intervals. So we would say negative infinity to 0 would be the first place you're concave up, and then from 2 to infinity, so you can write that interval like that. Okay? Concave down, where did that happen? 0 to 2, right? Right in the middle. Okay, so you write that interval as 0 to 2. All right. Now, what I did, I think your handout, I gave you a graph, is that right? Okay, I usually try to do that on your handout just so you can make sense of this. So what happens on the graph, I graphed the function, and that's the graph of the function. So you can pretty well see on here that when you're below 0, doesn't that look concave up? Okay, it's got half of a smiley face. And then from 2 to infinity, is that concave up? Indeed it is. Okay, isn't that cool? And then concave down is there. Okay, so what the graph is doing is it's going from up to down to up like that. So where are the points of inflection? In other words, where does the concavity change? 0 and 2, right. Now, if I want a point of inflection, I want you to give me a point. Okay, so we got to get a point on the graph, and we can use the calculator to help us a little bit with this. So one thing we have is that would be an inflection point, and that would be an inflection point. So we have 0, and then we have 2 like that. Okay? Now, one thing you can do on this, I want you to be able to do this with arithmetic as well, but you can also just take advantage of your calculator and do that too. So I'm going to go ahead and do that on this problem. And I'm just going to put in, you can do this with me if you want to. We're going to do like 5x to the 4th, and then minus 20x to the 3rd. And let's see, plus 10. So a lot of times, I want you guys to be able to do arithmetic, obviously, but when you're getting a point in an inflection, I want you to know the y value too. So what I'm going to do is just do this in a standard window, and you'll get roughly the same graph I have here. I don't remember what window I used. I probably changed I changed my window. One thing that's kind of helpful to know, do you guys know what the significance of that 10 is in the function? That's a y-intercept, right? That is the y-intercept. Anytime you have a polynomial, that constant term's the y-intercept, so it's intercepting at 10. But anyway, what I'm going to do is I'm going to do this. If you want to fill in the point, all you got to do is just type trace the first inflection point 0. So you have a point 0, 10. Okay, so that would be your first point of inflection is that. Then type trace, type 2. That inflection point is negative 70. Okay, so you can do that arithmetically, but your graphing calculator will save you a lot of time, don't you think? Okay, so I'd recommend you know how to do both, okay? All right, so that's the end of the problem. Everybody got that okay? Okay, so graph them on the calculator if you want to. Otherwise, all I'm really doing on this is to get that negative 70, I'm just doing 5 times 2 to the 4th minus 20 times 2 to the 3rd plus 10. Okay, that's all I'm doing. But the trace will save you a little bit of time. And also, it'll give you the ability to see if you're on the right track with your answer. Okay? All right, any questions so far with that one? Okay, that's probably as simple as these problems can get. Okay, straightforward. Okay, next one. Now you get into an exponential. So it can get a little bit trickier when you get into an e to the x or a logarithm or something. So again, if we're going to analyze the concavity, you want to get the second derivative. So let's go ahead and start with the first derivative. Okay, how are you going to do the first derivative? This is the product rule. So you can go ahead and start with your product rule if you want to. So that is first derivative of second is 1 plus the second, x minus 3. Derivative of first is e to the x. Okay. Now what I would recommend doing is just sort of clean this up before you go to the second derivative if you can. I'm going to just write that as e to the x. I'm going to distribute this to get x e to the x. And then I'm going to get that as minus 3e to the x like that. Okay? I like to kind of simplify things to make my second derivative easier if I can. These are like terms, right? That's 1 minus 3. So that's negative 2e to the x plus xe to the x like that. Okay? And now we can differentiate there. You could even factor an e out of that if you want to and do it that way. Okay? Won't make that much difference. In fact, I think I'll do that because that might make it a little simpler. Okay? What's that? Yeah, exactly. I could have actually done that at the very beginning. I could have taken e to the x out. Okay? Let's do it now. But it really doesn't matter. You'll get the same answer anyway. So we have a common factor of e to the x. Like this, so take it out, so that'll give e to the x, and then negative 2 plus x, or e to the x minus 2. So I like that first derivative, okay? Now, if we were doing increasing and decreasing, if I asked you to do increasing and decrease and look at mins and max, then you would do your sign chart based on the first derivative. But since we're going to concavity, now we want to go ahead and we want to take the second derivative for that analysis, okay? All right, this is product rule again, isn't it? Okay, so let's do that. Okay, the first is e to the x. The second would be 1. Derivative of x minus 2 is 1. Then the second's x minus 2. derivative of first is e to the x. That's a pretty basic product rule problem. Okay, now what you could do, I'll do this one a little different. I didn't see this when I was doing the first one, but couldn't you just factor an e to the x out right now? Okay, that's what I'd do. Okay, all right. So what we do is we have e to the x, and what's left in that bracket? 1 plus x minus 2, right? Okay, if you take the e to the x out, right? So that means that's going to give e to the x, and then you're going to have x minus 1 like that. Okay, so that's the calculus part of that. We've got our derivatives done. All right, everybody okay with that? Okay. Now, what you need to do is you always need to do this when you're looking at concavity. You need to do two things. You need to figure out where is the second derivative 0 or where is it undefined. All right, is this thing ever undefined? What do you think? No? Okay. E to the x is always defined, right? An exponent can be anything. So what you do is you move on, and then you just do e to the x, x minus 1 equals 0. So you're ready to solve that equation to find how to break your sign chart up. Okay, what is one answer that just jumps out in your head?
1.
Hopefully 1, right? Okay, because you got two factors. You have e to the x equals 0, then you have x minus 1 equals 0. Well, this factor here is going to give you x equals 1, right? How about this one? If you solve this equation, do you get anything out of that? No. Students a lot of times overlook that. And the thing about this is, if you take any number to any power, you never get 0. Never happens. Any number to any power is never going to give you 0. Okay? Or if you didn't know that, because sometimes you won't, I'll tell you exactly what happened. You might think, oh, I take a log of both sides. Can you take a log of 0? No. So the math doesn't lie to you. Okay, it's going to tell you there's no answer to that equation. So what that's going to tell you then is basically we're now ready to do our sign chart, and all we got to do is just work with 1 like that. So you want to go ahead and draw a number line, and then you have x equals 1 like that. Okay, and that's where the second derivative was equal to 0, was at 1 like that. Okay. All right, so now we're ready to do this analysis, and what we're going to do is we're going to use the simplified form of the second derivative. That's e to the x times x minus 1. So now it's just a matter of doing test points. So I'm going to use like 0 there and say 2 there, just to keep it as simple as possible, okay? So what we're really doing is plugging in here, so that would be e to the 0, 0 minus 1, that would be 1 times negative 1. That's negative, so what does that tell about the concavity? Or concave down, okay? We got some kind of a U shape kind of going down, kind of like that. Okay, then if we plug in a 2, we have e to the second times 2 minus 1. E to the second's definitely a positive number. 2 minus 1 is a positive number. So this one means you're going to be concave up, like that. Okay, so that's how that works out. All right, so what we would do then is we can go ahead and do our interval. So concave up would be 1 to infinity. Okay, and again, what we do on that is we use a parenthesis, and we say 1 to infinity like that. Okay, and then concave down would be like this. So we would say negative infinity to 1 like that. Okay, where is the inflection point located? X equals 1, okay? All right, so it's x equals 1. And again, I want you to write a point, not just x equals 1, we want to write a point. So what you need to do to get this y value, you need to go to the function, and you need to evaluate the function. So you're going to do f of 1. So go way back to the beginning. That would be e to the 1 times 1 minus 3. So that is e times negative 2. So that's negative 2e. And I want you to write that, exactly. Okay, if you traced this out on the calculator, you wouldn't get a negative 2e. You would get the decimal equivalent. So you want to be able to get that exact answer like that. Does that make sense? Now I went back to the function because I want to know the y value on the function. So what you have is this inflection point right there is 1, negative 2e. All right? And if you look at the problem, the sign chart said you were concave down here. Does that look good to you? Okay, it said you were concave up here. Okay, does that look good? Okay, all right, you got it. Okay, so that's the idea with concavity. You're looking more at a shape of a graph, given the overall shape. All right, is there any question about that with anybody? Okay, those weren't too bad. They can get pretty nasty if you have a second derivative that's kind of complicated. So these aren't too bad. Okay, on the next page, the other thing that I want you to be able to do is these activities right here are more, do you understand the concept? So I like to kind of spend a little bit of time on, I give you clues, can you draw a graph? Now these clues are going to have something to do with either increasing, decreasing, or concavity now. So this is the mathematical detective time here. Okay, I give you clues. You find the missing function. All right, so here's what we have. Can you tell me what this would mean? The first derivative is greater than 0. What does that mean?
Positive slope.
Means what? Positive slope, but what does that mean the graph is doing? Increasing. Good. Okay, so you might write a note to yourself that the function is increasing when, well, it doesn't, so hold on, it just says, hold on, did I give you enough clues on this? Okay, I got to say it's increasing on something. Maybe I didn't write this problem down right. That's what I have a feeling. Okay, maybe we'll just make something up. Okay, how about this? What does this tell you? The second derivative is positive. What is that? Concave up. Okay, so you are concave up at some point in time. See, the thing is, I should have given you this. This isn't enough. I have a feeling I didn't copy the whole problem. Okay, so let's add this to the problem. Let's say f prime of x is greater than 0 at x is greater than 1 or something like that. Okay, or and then let's say that we're concave up at some other point like that. Okay. And I'll have to make this up as I go. So let's go ahead and let's draw a graph. I know that's what I did, so I didn't copy that right. Okay, so let's say that at x equals 1, you know that you are increasing. Now you can increase in different ways. I mean, you could go like, it could be a line, it could be more like a curve, it could go more like that. There's a lot of ways that you can show that a graph is increasing. And then when you're concave up, well, there's several ways you could do that. It could be a whole interval like that. It could be like half of a smiley face like that. It could do something kind of like that. Or it could even look like this. So when you're doing these problems, you want to know that there's different ways the function could look when it increases and different ways it could look when it's concave up. So if we're going to be concave up, we're going to, and I'll just say on this, I'm going to try to just make something up here. You know what I think this problem meant? I think this problem meant just on the interval negative infinity, infinity. I know that's what that meant. So let's just add in that the problem also was supposed to contain that it was this way on all real numbers. Okay? So let me ask you a question. If you look at these three possibilities for concavity, which one would be the one where you would be increasing always and concave up at the same time? What would it look like? Kind of like this one, right? It'd be like this. So you would have to have a graph that looks like this. All right? So let's just, and you can draw it however you want to. So if you did that, then that would satisfy the conditions of the problem. You would always be increasing and you would always be concave up. Does that make sense? Okay? I think I left off this piece right there on the problem. Because if I don't give you that, I'm not giving you enough information to nail it down to a graph, really. Okay?
So it's always those six options, though.
What's that? Yeah, absolutely. Like concavity, and this is a real important thing. If you're concave up, it's either going to do that, that, or that. If you're concave down, it's either going to do this, this, or this. It's just like an entire frown or half of a frown. A concave up is an entire smile or half of a smile. That's the way I look at it. Okay? All right? All right, well, let's do this next one. I think I've got all the information on this then. All right? Okay, so let's kind of organize what we have here. So this is the first key statement right here. It looks like we kind of got two key things. And this time I did give you an interval, okay? All right, so tell me what this statement right there tells you about the graph.
Decreasing.
Decreasing, good, excellent. Okay, first derivative's negative. That means that the function's decreasing. Outstanding. What does this second statement say?
That is a concave down.
We're concave down, good. Okay, remember we could look any of those three different ways. Okay, go over here. What does this statement say? Still decreasing. Okay, and then what does the last statement say? Concave up. Okay, so we have everything we need. You kind of, partially this activity, what it's trying to get a student to do is understand the definitions and then be able to put something together. Okay, well the key interval is, the intervals that are important on this are negative infinity to 0 and 0 to infinity. So what's going to happen here, in this part of the graph, you're going to be decreasing and concave down. Okay, now I want you to look at, let me just stand up here, I get tired of sitting all the time. Okay, so if you were decreasing and concave down, which one of these would it be?
So decreasing concave down.
They'd have to be like that, right? It would have to be decreasing and concave down, okay? Now over here, you're decreasing and concave up. Which one would that be, decreasing and concave up? It'd have to be that one, right? Okay, that's why to me it's kind of important that you understand that concavity can take these shapes, okay? And that kind of helps you put it together. Now see if you can draw just a possibility. You can be creative as long as it's establishing those shapes, you're okay. So yeah, this, if you're decreasing and concave down, that would have to be that shape. So if you drew the graph now, it would have to do something kind of like this. So and you can just do something kind of like that if you want to. Okay, something like that. Okay, then what it's going to say is, let's see, if we're decreasing and concave up on this interval, then you'd have to look like that. Okay, so if you do that, then you would have to have some sort of change kind of going like that. That would be one possibility. It'd be like that, right? So here you would be decreasing and concave down, then you'd be decreasing and concave up. That's one possibility.
You have a separation.
What's that?
You have a separation.
Yeah, you could have that too. Like what he's drawn, you did what, something kind of like this, maybe with an asymptote or something. How about something like that? Would that be possible? Okay. There's more than one possibility, but
You just have to get it on the graph.
yeah. Right, you got to show that your graph is a possibility of that, okay? And I didn't say anything about an asymptote, but you could certainly put one in there, okay? So you could do something like that, all right? All right, does that make sense? Okay to everybody? Okay. All right, well, that'll wrap us up on